Hello, hi. Thanks a lot, Makiran, and thanks for the introduction. And also, I thanks to the HybridNeuro community to give me the opportunity to talk about my research while I'm present in this lab. Um, so, uh, so basically, I've been here like 4 years now, and I've tried to actually. My research has been like a more like a. So I've worked in like in different subjects. So today I'm going to talk about like some the studies. So basically, I've grouped them together into like three major parts, or maybe like two actually. So one is the experimental, which is based on animal models, like validating interface on animal models, and then development or fabrication of neural interface. So starting like I started working in this project from EPSRC. The project is coined as NISNEM. So we are trying to record single neuron activity from the brain non-invasively. But then to achieve a non-invasive recording and to fabricate novel interface, we need to do some invasive studies. And for that, we have to choose a model. And for the model for today, or for this experiment, or for the project, was the mice. Um, and this was like after like a many like hours in the workshop by another team and also by our lab, we have come across this electrode is made of conductive elastomers. So conductive elastomers is like a rubber-like material, is very biocompatible and it's very flexible. And you make it conductive by introducing like metal ions inside the rubber material. And we have this 8x8 array, and diameter of each electrode is close to 80 micrometers, and the pitch is 130. And the total area, so the total area of this is around 2.5 by 2.5 a millimeter square. So it's like really tiny. And so this is like the electrode we have come up from the project, and we need to implant them on the animal model. So basically, to validate a novel neural interface, when you make them, you go for the basic experimental protocol. For us, it was you perform craniotomy on the animal, you place the electrode on the sensory motor cortex area, and you try to stimulate stimulate the peripheral nerve, or try to stimulate the largest muscle, and see if you can get any recordings in the brain region. And to the right, we can see it's like the stimulation triggered average of the channels where we got the response. And also we have examples of other channels where it was like basically there was no response. So basically you have the brain, the cortex, and then you place the electrode on top. You're stimulating the peripheral nerve, and you can see the heat map. Only some of the electrodes are active, showing that it's like selectively actually recording from the sensory motor cortex of the animal. And also like it's also very important, like when you have a novel neural interface, you compare your interface with a known or a commercialized interface. For that, we have for comparison, we are using an array from NeuroNexus, and this is basically almost similar. It's 32 channels. It's a 32 channel array, and it's made of polyamide and metal. Diameter is a bit larger, and also the pitch distance is larger. And so we have performed similar studies. So we have stimulated the sciatic nerve, and we have recorded to the cortical region. But for this protocol, we have also tried to induce seizure by inducing AP4 drugs. So to the right on the top is like before. So we just you just apply a tiny bit of drug to the open area of the brain, and after 10 or 15 minutes, you see the activity. So we can see, even though when the electrodes are tiny, you can still record like this the natural phenomenon. So as a recap of what our electrode, the NISNEM electrode, can achieve against the commercially available ones, the NeuroNexus. NISNEM electrodes, the electrodes are really tiny, and the pitch size is also like really small. We are optimistic that with this kind of diameters and the measurements, we might be able to actually measure single neuron activity. So this was the experimental part, and then a bit of electromyography. So probably everybody in this room knows more than what I know. So a bit about like the types of EMGs we can record, the surface and the intramuscular. So there are like both advantages and disadvantages of recording like whichever method you choose. But if you are going for the intramuscular EMG recordings, you're gonna get like a very high quality signal, and there's no distortion like say like crosstalk. You can avoid crosstalk between the muscles while recording from your intended muscle. And the only drawback for the intramuscular is a bit of invasive, but it's like very minimal, and then it depends upon the type and the depth of the muscle you want to record from. So this the slide here is to the right. This is what Elon Musk is trying you to believe in, right? And so he's telling we are going to implant chip in the brain, right? Are you really interested to get an implant in your brain? Maybe, maybe not, huh? So, and to the right is like the labs, like the conventional labs who are trying to get this human-machine interface working by using the peripheral nerve. So both of these techniques it can give you very rich signals, but it comes as a cost of very like invasive high-risk surgery. But then our lab or like here, like in the community, so we know like we can actually decode the intracortical activity by using from the surface EMGs or also from the intramuscular EMGs. And the best way and some of the advantages of this method over the direct interfacing with the brain or going for the nerve is very easy to implant the intramuscular electrode. It's just a pinprick and you get the electrode in your muscle. And you can go for multiple level implantation, and you can start recording immediately after you implant the electrode. The signals are very good, and also you can have multiple implantation in the same muscles or different muscles in the same time. And then once you are done, you can just take out the electrode and throw it away. That's it. So if I try to convince you, okay, this is like the technology is one of the best, like the intramuscular recordings. So we need to support it. And so like the people from the lab, especially Agnese, she had made this platform where we can validate the intramuscular electrodes. So our idea was how fingers can be controlled by the motor neuron perspective. Also, can the motor neurons extracted from the intramuscular EMG electrode provide a higher classification accuracy than the other time domain features? So we use this the platform, and we used isometric finger flexion and extension for like individual fingers, and we did some combination movements to identify motor neurons and their activities during the tasks. And when we decompose those intramuscular EMG signals, and then we used some separation of vectors across the recordings, and we found the single digits and combination digits are mostly defined by unique motor neurons. And so this information actually gives us can be used as a feedback or can be used as a control for more precise hand gestures for prosthesis or for a human-machine interface. And also with this info, we built some classifiers, and it shows almost 100% accuracy over 6, 8, and 12 classes. So this was a bit of like the EMGs. just to convince intramuscular EMGs are much better. Means are better, not much, are better than the surface EMGs and far better than going for the brain implant or targeting directly to the peripheral nerve implants. So this is like the main topic, or what I specialize in is like building electrodes, especially the intramuscular electrodes on thin film technology. As some of you already know, our lab uses thin film. So thin film, this is from Fraunhofer Institute from Germany. So, and each of this costs you around 2K, 2000. Okay. And so actually, this was like Dario's vision and Dario's encouragement. So we can actually use the Imperial clean rooms to build our own electrodes. So we can stop dependent on like third parties. And also we can customize the electrode whenever we want. And also it's going to be, we can improve the design. We can actually build this electrode across different muscles and also across different different models, animals or humans. And if you want, we can actually make those 1D array. This is like one-dimensional array. We can make them 2D, basically. So a bit, not to like is overwhelm you about this is the fabrication steps. So just remember like the three main major like steps to fabricate thin film electrodes or mask fabrication. So you design like what according to the requirement, paying attention to the resolution and the limitations of each machines and the metal patterning, like whichever metal you want to use, the final steps is a platinum, gold, and how the metal should stick to the polymer structure, and lithography. These are the lithography. These are the three basic and also very critical steps of for microfabrication. And the entire process is like combination and permutation combination and mix of these three steps at like different times and different conditions. So to your right, this is the fabrication process which is used or which was and is used by Fraunhofer. And to the left is the Fraunhofer technology, the original process to manufacture thin film. And to the right, this is the current process which we are using. And you can see basically we have cut down a few of the steps of the fabrication process. And if you cut down few, and if you are capable of actually reducing the steps, you are actually saving time, and time is money. So and also to say, since I was talking about, since we have the freedom to actually design our own electrodes, we have actually made electrodes both for animals and for humans. So the human electrodes is almost similar. We kept the Fraunhofer designs, and for animals we have changed the parameters of pitch and the types of electrodes. Moving on to the results. So what happened when we did the for the first time? So the first time we followed the process of Fraunhofer actually. We looked through the microscope. Everything was good, like nice. So we have nailed down the process and the recipe. But we went a bit further. Same electron, we found they were like it was not really good. So the gold was peeling off from the substrate. So and Fraunhofer uses wet etching. So etching is a process you remove the excess material from the substrate. This wet etching, and our labs or the clean rooms at Imperial are actually not good for wet etching. There are so many circumstances, but it's good for like dry etching. Some of all the again like so we have like many setbacks. So but the setbacks, so to the left, polymer, so we had some the polymer was somehow cracked, and then you can see the polymer was destroyed while curing. So there's like a crack formation on the wafer. And the middle one shows when there was like poor addition between the silicon wafer and the polyamide, and we went for the final step, it actually basically ripped off from the substrate. And the third one is like etching. So if we have too much etching, so we have to etch to remove the excess parts. But if we etch too much, the gold disappeared. So it was like so we had to play with this type of parameters. We had to come with our own recipes all the time. And finally, we did manage to actually build like a number of electrodes. This is like it shows the complete fabrication of the electrode. And these lines, this is the final step, is like you laser cut the individual devices from the wafer to realize the individual electrodes. And so this is like some of the microscopic view of the electrodes. It shows that these are like the exposed gold and exposed gold here for the electrode sites, very clean. And the final result is at the bottom. This is the one complete device. And now a bit of a comparison between the Fraunhofer fabricated and the Imperial fabricated. Basically, we have tried to keep the same design, but and also like for our we are actually making some changes in the design so that we can use different amplifiers than the ones which we are using in the previous days. And also, like, we need improvements. We are like pushing for improvements for our own devices. So we do have the capabilities and the clean room at Imperial to make those electrodes 3D, just to improve the signal to noise ratio and to also get a better contact of the tissue from where we are recording. And we have also planning to coat the electrocytes with a P.PSS. It's like special material, and also or platinization, just to increase the surface area, so that we can increase the surface of recordings, and also it brings down the impedance of the electrodes. And the last one is to increase the power of the signal at the source by designing the electrode so that it behaves as a transistor. Just to wrap up everything, so these are like a few of the people I would like to thank for providing me with like valuable information, and also like particularly Dario. He gave me this freedom and opportunity to actually pursue this project, and that's it. So yeah.